Hi. So let's start now with the notion of degeneracy. So we saw the case that when we're thinking about how we form vertices, um, and we looked at the way we do so is by intercepting n constraints in Rn. But it might be the case that sometimes you have more than n constraints that are active in a given vertex. Like in R2, you can have 2, 3, or even 4 lines crossing and forming a vertex, right? And because everything we build is based upon this notion that we are doing this one-to-one connection between n active constraints having n linearly independent vectors, and that procedure we just seen that we pick n minus m variables and set them to 0 to then form a basic solution. This clearly might have troubles, might have it might pose challenges to us whenever this is the case, and that is a fact true, and that is actually one of the reasons why the simplex method can be made inefficient if it's the way you have to handle you decide to handle degeneracy. And degeneracy is exactly that. Is it when you are in a situation, say, like in this case on the left, where this is a problem in R2, but what you see here is that while these are all regular basic solutions, these are the basic feasible solutions even, this point here is a troublemaker, because this point here has 1, 2, 3 constraints forming it in R2. And the issue with that is that for this point, for example, or even this point, there is another troublemaker here because it's 1, 2, and 3. So for this point, for example, it's clearly specified when I say it's the intersection between this line and this line. It gives me this unique point right there. But the problem with degenerate points, especially degenerate basic feasible solutions, is that whenever I'm trying to represent B, I can say the B is, say, the intersection of this constraint or this constraint. But it also could be the intersection of this constraint and this constraint. So there are multiple pairs of constraints that take me to the same vertex. And that is a problem if I can't really see my geometry, right? I can't really see these figures when I'm looking. That we are looking at only working with an algebraic representation of it. So this is a basic degenerate basic BFS, basic feasible solution. This is a degenerate, but it's not feasible. So the problems when they are degenerate and also feasible. Here is another example, a polyhedral set that will be formed by the intersection of this constraint, this constraint, this constraint, that constraint at the bottom, and there is a constraint at the back. And same thing. This is a regular vertex. It is a BFS and it's formed by 1, 2, 3 constraints. But this is a troublemaker because it's formed by 1, 2, 3, and 4 constraints. Okay. Here is a numerical example. So how can we see degeneracy in a algebraic setting when we can't see the picture? Like in this problem, that is a problem in R7. So let's look at the base 1, 2, 3, 7. So I'm picking columns 1, columns 2, columns 3, and column 7. Do the same procedure. That becomes my matrix B. I solve to find XB. XB for 1, 2, 3, and 7 is 4, 0, 2, and 6. And then when I put together with the non-basic variables of 4, 5, and 6, I get this variable, the vector x. But look at something was off here. When I solved the system for the basic variables 1, 2, 3, and 6, one of my basic variables was set to 0. So instead of having 3 variables set to 0, 1, 2, 3, what I actually have is 4. So it's not n minus m, but n minus 1 plus 1. So the algebraically, to see degeneracy is when you look at a given basic solution, at a basic feasible solution, for example, and one of my basic variables stubbornly takes value 0. That's an indication that this is a degenerate solution. I have 4, not 3 intersections of constraints. So another example here, 1, 3, 4, 7. Same story. My matrix be 1, 3, 4, and 7. And when I solve for x, I get 1, 3, 4, and 7. I get the same 0, yeah? So it's also non-degenerate. And now look at the value of x here, and look at the value of x here. At exactly the same point in R7, 4020006. And why is it the case? Well, because when we make a basis, we are expecting to land on a vertex, right? It just so happens that these two bases represent the very same vertex. So geometrically, they are the same position in space, even though they are formed by different subset of constraints. And that's the main problem with degeneracy. It might, one of the main problems. It might make you, if you have this method that keeps taking you. Notice that these are adjacent as well. So this 1, 2, 3, 7, 1, 3, 4, 7. So we basically swapped 2 with 4. So we went from one basis to another, at least you thought so, but in terms of space, you never left. You are in the same vertex. So this can lead even to even more complicated things, and where you have more and more dimensions, like the problems we'll be solving with a few hundred variables. You can keep going around and around and around and around different bases that but never leaving the same point you were, because you're just going around degenerate bases that are not adjacent to they are adjacent bases, but they are the same point. And also, just a point, a remark for the future is that degeneracy, it might be representation dependent. It might be so that you can change your formulation to get rid of degeneracy. So here is a very simple example where I have this problem P1, where I have this constraint x1 minus x2 equals 0, and this other constraint, equality constraint here, and then assume that these two variables are greater than or equal than 0, but I don't do it with x1. Because x2 equals x1 and x1 is presumably greater than or equal than 0, in principle, I wouldn't need it, right? But if I do, you can see that as soon as I add this constraint to the consideration, I make my 001 point degenerate. So, for example, this point here becomes the intersection of this constraint being 0, this constraint being 0, and the line represented by this constraint, or even this constraint, sorry. There's another plane here that we're not seeing. That's where this is lying. But anyway, so this is showing that this intersection for x2 greater than or equal than 0, if it wasn't here, it wouldn't make this point degenerate. So it's representation dependent. In the sense, it's kind of connected to what we just seen, with the sense that redundant constraints, they lead to the same polyhedral, and it might be so that removing that constraint, you get rid of degeneracy. So it's a very good idea to if possible, get rid of redundant constraints. All right, so now we move to the second part, which is now looking into the notion of optimality for extreme points. So we'll just talk at first about how do we show the existence of extreme points under an algebraic standpoint, and then how do we recognize whether they are optimal or not. So let's go. So let's first, define the situation in which we can guarantee the existence of extreme points, those points that we know there are candidates for optimal solutions. And it's sort of an algebraic setting. One way of looking into it is this notion of the containing a infinite line. So an infinite line is an unbounded one-dimensional set, basically, in Rn. So we say that the polyhedral set P contains a line if it's not an empty set, and if there exists a non-zero vector D, such that doesn't matter how far you go in that direction D, you're still within the set P. So basically means that you have this infinite line that you can carry on going on forever without leaving the set P. So that's the notion of containing a line. So Rn contains a line by definition. two parallel lines in Rn. Suppose this is my polyhedral set. This contains a line in this direction, in direction that is parallel to them. So this is the notion of containing a line, and we can use that. You know, it's a tool to prove the existence of extreme points. And so the proof of this proof is, it's in the textbook. We're not gonna visit that because it's more like a geometrical thing. It's more for people who are interested in say convex analysis and polytopes and things like such. So I'll give you a proof by picture, because honestly the consequences of that for what we're doing are not so important. But basically the story is like this. If you don't, so the following three are equivalent. Let our set be polyhedral set be defined by a collection of half spaces, like so. So if P doesn't contain a line, it is equivalent to say that it contains at least one extreme point, and if it contains at least n vectors that are linearly independent. So we've seen the connection of these two before. The fact if this extreme point is a basic solution, basic solutions connect to having linear independent. And the one thing missing is the story of connecting a line. But there is what I'm gonna give you a proof by a picture. So we have a theorem 14 from lecture 2, that says that if you have a vertex, you have extreme point, right? How do you form a vertex? You form a vertex when n hyperplanes intersect. Okay. If two hyperplanes intersect, there is no way you're going to contain a line in this space anymore. Because, so we are in R2, right? As soon as you have two hyperplanes that are not parallel, they are going to intersect at some point. And once they do, there's no way you can contain a line anymore. There is no line you can draw here in this direction, or even in that direction that would be contained because of this. And because you now have a vertex, you have extreme point. And that's just that. So you can use this notion of containing a line to try to see whether there exist extreme points in your vertex in a geometrical sense. But again, that's not very important for us. But it's just to show a connection that it's kind of an easy concept to see visually. So I have here two better drawn pictures showing that. So this is a polyhedral set that contains a line, and therefore you can't see any vertices in it. And once we look at this set has two extreme points and cannot contain a line. If you try to draw a line here, you see there's no way you can draw an infinite line. The catch, or the reason why we're discussing these, it's actually the following. It turns out that whenever we're looking at our optimization problems, or linear optimization problems, we can always assume a bounded polyhedral set. The reason for that is because we're going to be solving these using computers, and in computational settings, everything is bounded. You don't have infinity. You have really large constants, but they are infinity. And more in engineering problems, you can always set boundaries for variables. How much product you make, how much product you buy. You can't buy infinite products. There's always a big number you can put there. So in a practical setting, a very pragmatic, we're always talking about bounded polyhedra, and bounded polyhedra will always contain lines. So therefore, there is always going to be at least one extreme point, which is a candidate solution. Moreover, because we're always talking about standard form, and that standard form involves the positive orthant, there you go. You're always going to have an extreme point. 0, 0 is always a basic solution. Might not be feasible, but it's always a basic solution. Actually, the simplex method that we're going to see next week is based on that. It's built upon the fact that you can always count 0, 0 to be a basic solution. And it will not contain a line, right? And basically, in every non-empty polyhedral, bounded polyhedral set, and every standard form polyhedral set will have at least one basic feasible solution. They're always going to have one. If it's bounded, you can always find an extreme point. And if it's standard form, 0, 0 is your solution. Okay, so that's why I've said that this notion of containing a line is not the most useful thing, but it's a good thing to know anyway, and it gives an interesting geometrical interpretation. Now, the optimality of extreme points. We know that we know from that geometric interpretation we looked at our linear programs in the beginning of the course. We know that these extreme points are candidates of optimal solutions. So this is kind of what we already know, but what we're going to do now is to provide it in a more formal setting. But we know that if we have an optimal solution, it might be so that we don't have any feasible solution. It might be so that your problem is unbounded. You can carry on forever in that direction. It will always be within the set of extreme points of the feasible set. So that's exactly what we're going to prove with Theorem 6 that is coming next. And that is the theorem that we use as the stepping stone or the foundation for developing a solution method that only is going to investigate extreme points. And that's what the simplex method is all about. And that's kind of why simplex method is built like so, is because we have this theorem that tells us the following. So let P be just a polyhedral set defined as such, and C a vector in Rn. So assuming you are minimizing, you're solving the problem of minimizing this linear function C transpose X, where X is basically is inside this polyhedral set. So assume or suppose that P has at least one extreme point, and that there exists an optimal solution. By the way, it might be so, it's not obvious at first, but you might have a set. Say this is your set Q that I drew before. If your vector C is like that, so this is your vector C, you're gonna look for solutions. Well, sorry, if your minus C vector is like that because you're minimizing, so you want to go in that direction. If you're looking for solutions in that direction, even though you do have extreme points, your problem might not have an optimal solution. So that is why we have this that and that there exists an optimal solution. Okay. Then there exists an optimal solution that is an extreme point of P. So basically, if you have extreme points and you can find an optimal solution, you're going to find an optimal solution that is an extreme point. This is basically the most fundamental theorem for developing the simplex method. So one of the exercises is going to be that you're going to look at is going through the proof of this, because it's a bit more involved and you kind of have to be concentrated to do that. So I'd rather do it in a dedicated setting. But that's an important, very important theorem that we're going to revisit a couple of times. And that's basically telling us if you have extreme points and this problem is solvable, the solution, the optimal solution is going to be an extreme point. And that means let's only look at extreme points then, which is upon which everything we're discussing so far, and we're going to discuss the next week as well, is based on. So yeah, so let's stop here. I think that's a good stopping point before we head to our third video. So I'll see you in the next video.